Hello, welcome to Notes on Evaluating Piecewise Functions from a Graph. I wanted to talk about piecewise functions in the context of some real-life data. You'll notice that piecewise functions have a lot of pieces, so they're useful for describing discontinuous or not connected or disjointed data. Not all info can be written so nicely with one graph, like a parabola, for example. Here we've got Netflix and Disney Plus subscriptions, as well as their sales, or I should say, their earnings. For Netflix, it's been around for a while, so you can see how there are these generalized trends in its data, and they've been generalized with these lines connected together, and every now and then a line will have a different slope from the other one. And the same can be said for Disney Plus pre-sales. This is just last year over the span of, it looks like a month. And it's right before it was released. You can see how many people decided to, at the announcement, decided to go ahead and buy themselves a Disney Plus. And then as the launch came closer, you saw how many people took advantage of it. And we can't describe these types of graphs with just one function. So we have to connect a bunch of those functions together. And that's why we have piecewise. So if we were to compare Netflix to Disney Plus sales, we can tell which one is growing at a faster rate. It looks like Disney Plus, while Netflix is still pulling in more money from their subscribers. So there's a few different scenarios we can look at. If you're in physics, then velocity, acceleration, position is generally used with these piecewise functions, but we're going to get into the nitty-gritty on how to evaluate them in this. Oh, I also wanted to include more of a nonlinear example. Here are the interest over time. This is with Google Trends of these different dishes. So we've got pho, ramen, and soba, and you can tell that ramen is more popular worldwide, and in generally pho is more of a Vietnamese dish and not discussed as much as ramen, which is more popular. And you can tell that there would be a lot of different piecewise functions to graph here if we were going to analyze this data and figure out, well, what's happening at this time and so on. Alright, so looking at our notes, we have a lot of terms to discuss in order to be able to talk about piecewise functions and their graphs effectively. And this is going to round out our standards for how we evaluate piecewise equations and their graphs. Piecewise equations with a different video. But here in this table, I've got some terms for us. The continuous part of a graph is one that doesn't have any breaks, holes, or asymptotes. A discontinuous part of the graph would have at least one of those things. And then a cusp is a sharp turning point in the shape of the graph where two different slopes meet. So think absolute value vertex. A hole is going to be signified by an open circle, and it's going to have a continuous part of the graph on either side. So it's going to look like the continuous graph has just been punctured, for example. And then our endpoint is what we've been dealing with, domain and range. It's got points that are signified by a closed circle or an open circle, if depending on if those points are included or not included. And then any type of break is a vertical or horizontal asymptote, or a separation of x and y in the graph. You might also see this as a jump if you were to take maybe a quiz somewhere else on a different website, like Quizzes or Khan Academy. Displaced points are points that are not connected to another continuous part of the graph. And if we were to take these terms into this example for f of x, our breaks would occur at x equals negative 1, and at x equals 3. And while we're here, this point is 3.4. And this point right here is 3, 2. If we're talking about the domain and range of this entire piecewise function, then we're going to use these breaks to help us determine it. Are all values, if we just take this green piece, are all values from negative infinity to the end of this green piece in the domain? No, they're not. So I'm going to break my domain at this open circle, which we'll discuss in a second. So this would be from negative infinity to 1, parentheses, and join that with a union to the rest of this function. Now, does the rest of our function break at all in its domain? Are all the values included in the domain? Yes, they are. Even though this is a jump or a break, like we discussed earlier, because we have a separation between y values here. There's an open circle. That means there is a value at 3. It's 3.4. And then we start back up with our y values at 3, 2. And we continue on with them. So the rest of this domain is -1 to infinity. And then our range for this function is going to go from the bottom and we'll work our way to the top. Negative infinity is in our range, and we look at our breaks and we say, okay, is this y value included? Is it included anywhere else? Yes, it's included here, and it's also included here. So that y value is in our range. And then are all these y values in our range? Yes, they are. They're over here, they're over here. They're in a few different spots. And then we see this arrow up here. So our range is actually negative infinity to infinity for this function. The cusps that we can see on this graph are at x equals 0 and x equals 1. We can point out their xy locations. This is 0, 6, and 1, 2. But you can tell that there is a distinct point to the graph at these spots. And that's because there's a sharp change in slope. The holes in this graph are at -1, 2. So this first break that we found was a hole. And this over here at 3, 2 is not a hole. It's just a break, signified by two different endpoints jumping past each other. So now we're at endpoints. We have endpoints at 3, 2 and 3, 3.4. And we want to figure out, is this piecewise graph continuous or discontinuous? Why not? Why or why not? This piecewise graph is discontinuous, and that's because we have breaks. No, because there are breaks at -1 and 3. So another crucial thing to point out here is the domain and range are independent of some forms of breaks. So our domain was not interrupted by a break in the graph at x equals 3. So be careful equating a break in your piecewise function to something directly related to domain or range. That'll have to be something that you observe on the graph. And lastly, with this function, I wanted to evaluate this piecewise function, which I've put in small scale, at the given values. So at -1, that's where our hole is. There's no y value. So if we were to plug in -1 to this graph, we check that x location and say this is undefined because there is no y value that goes with that x value. At 0, we look at the cusp, so that would be 6. At 1, we also look at the cusp, that'd be 2. At 2, we look at our square root piece, that's 3. And then at 3, we have that break. This is a difficult one to pick, but not if you follow how these points are noted. This is a closed circle at 3.4, and an open circle at 3.2. So we will be taking 3.4 as our y value at 3 because it's a closed circle. So we're going to ignore the open circle because it's not included. And then for 4, we're at the vertex of our parabola at 1. And then number 9, what's happening on this graph at 9? We actually need the purple piece of this. And given that there isn't any more stretch to it, this quadratic is just moved right 4 and up 1. So if we can use this equation, we can figure out what is happening at 9. Very cool. So that's also noticing how transformations fit with these piecewise functions. Alright, so in this last part of your notes, I'm going to just look at one of them with you, and then I'll show the answers to my notes at the very end of the video, so you can see what I got for them. The crucial question here in this example is number 8. What's the xy location of this displaced point? We didn't have one of these in the other example. This displaced point is at -2, -2. And you can see how it's removed away from the rest of the function. So it's not a hole, it's not an endpoint, it's nothing like that. It's a displaced point. And so what I'm going to do for the rest of this is work through it really quickly and show you what I got for my answers. At the bottom there's an advanced question. If you want to attempt it, you can see how you do, but I'll have my answers posted with these notes. See ya!